Hi, welcome back to Chemistry Part 1. Today we're going to be talking about stoichiometry. You're going to need your periodic table and your calculator to complete these problems. We're going to start off by looking at a balanced equation. And we're going to look at what a balanced equation actually tells us. In this equation, I'm being told that I have two reactants, CH4, which is methane, and O2, which is oxygen. Remember, oxygen is diatomic, so it's always going to have a 2 as a subscript. And I also have two products, carbon dioxide and water. Now, if I start with one methane and one oxygen, and I produce one carbon dioxide and one water, that's not going to obey the law of conservation of mass. So I have to balance my equation. We've talked about this before. I'm going to balance my equation by putting a coefficient of 2 in front of oxygen and 2 in front of water. What that means is that for every one methane, I'm going to need 2 oxygen molecules. And it's going to produce 1 carbon dioxide and 2 water molecules. So the coefficients tell you how many of the molecule, element, or formula units you have, and the reactants and the products give you the recipe or the ingredients. So we're going to relate this balanced equation to a recipe. If I have a recipe and it calls for 1 cup of sugar, 2 eggs, 1 cup of flour, 1 cup of water, and this is only going to be a partial recipe, but we're going to produce from these ingredients or these reactants 24 cookies. Now, if I ask you how many cookies can I produce if I have 8 eggs, okay, then I could produce 4 batches of cookies because each batch is going to take 2 eggs, and I can produce 24 cookies in each batch, and I could make 4 batches. So I could make 24 times 4, and that's going to give me how many cookies I can produce. Well, what we just did was we just did a simple stoichiometry problem. So what does the word stoichiometry mean? Stoichiometry is a branch of chemistry that deals with the relative quantities of reactants and products in chemical reactions. It's just like a recipe to cook something with. The only difference is that instead of cooking something that's edible, you're mixing reactants to form products through a chemical reaction. So why do we need stoichiometry? Well, stoichiometry, which is just a Greek word that means to measure elements, is going to be used for converting between different units, different chemical species and their units. So they're also going to be used for forming ratios between reactants and products and describing the ratios between the compounds, and for calculating the amount of product you will produce or the amount of reactant you will need to produce a certain amount of product. All stoichiometric calculations are going to begin with a balanced chemical equation. And this is where you're going to be given the amount of one molecule either a reactant or a product in the reaction, and asked to find the amount of another molecule. And just like with mole conversions, we're going to use a T-chart to do this. We're going to put our given in the upper left-hand box. In the bottom right-hand box, we're going to put the units that we're canceling, the units of our given, and then we're going to put the units we're converting to. We're going to keep doing this, or making conversion factors, which are just fractions that are equal to 1, until we're in the unit that we want to be in. Now, the reason we need a balanced chemical reaction is we need the balanced chemical reaction to get the mole ratio. So to convert from moles of one molecule to moles of another, the conversion factor is going to be the mole ratio. And the mole ratio is simply a ratio between the number of moles, which is the coefficients of two substances in a balanced chemical reaction. So if I have iron plus oxygen and I produce iron 3 oxide, I'm going to balance it by putting a 4 in front of iron, a 3 in front of oxygen, and a 2 in front of iron 3 oxide. What this tells me is that for every 4 moles of iron that will react, I will be able to produce 2 moles of iron 3 oxide. So how many moles of oxygen do I need to produce 2 moles of iron 3 oxide? Well, I'm going to look at the coefficient in front of oxygen, and I'm going to see that it's a 3. And so for every 3 moles of oxygen, I can produce 2 moles of iron 3 oxide. And this is what we call a mole ratio. A mole ratio can be written either way in a conversion factor. I can have 3 moles of oxygen over 2 moles of iron 3 oxide, or I can have 2 moles of iron 3 oxide over 3 moles of oxygen. Either way, I'm getting a conversion factor because I'm getting a fraction that's equal to 1. Now, try these yourself, making both the conversion factors that are possible from the question that's being asked. Then come back to the video and check your answers. So A says, what is the mole ratio of sulfur to chlorine gas? The reaction we're given is that S8 plus 4Cl2 produces 4S2Cl2. So I'm going to look at the coefficients. The coefficient in front of S8, there isn't one written, so that indicates that there's 1 mole of S8 and 4 moles of Cl2. So we can write our conversion factor as 1 mole of S8 over 4 moles of Cl2, or 4 moles of Cl2 over 1 mole of S8. We can also, for B, what is the mole ratio of oxygen gas to iron 3 oxide? We have 2 moles of oxygen, and that's going to produce 2 moles of iron 3 oxide. And so we can write our conversion factors as written. So exactly what is a stoichiometry problem and how will we solve it? Right here I have an example of a stoichiometry problem. How many grams of sodium chloride can be produced from 45.2 grams of calcium chloride mixing with an excess of sodium oxide. First thing is that when you say you have an excess, all that means is I have plenty enough sodium oxide to carry out this reaction. And so all of my 45.2 grams of calcium chloride is going to react. Now, where do I start? All stoichiometry problems, you have to start with a balanced equation. So I need to look in my problem and see what are my reactants. What am I producing by mixing what with what? So I am mixing calcium chloride and sodium oxide. So calcium chloride plus sodium oxide, and I have a double replacement reaction. So what am I going to produce? I'm going to produce sodium chloride and calcium oxide. Now I have to balance. Okay, so it should not be a 2 as a subscript. It should be CaCO. Calcium has a +2 charge. Oxygen has a -2. And so by putting a 2 in front of sodium chloride, that's going to give me my balanced equation. Now, my given is that I have 45.2 grams of calcium chloride. Before I can go anywhere in my given, I have to convert it to moles. Since my given is in grams or in mass, I'm going to use the molar mass from the periodic table. To convert it into moles. If it were in particles, then I would have to use Avogadro's number, which is 6.02 times 10 to the 23rd. If it were in liters, and remember I can only do liters if I have a gas, then it would be the molar volume, which is 22.4 liters. So in this problem, in this example problem, I'm starting off with mass. And I have to convert to moles. So I'm in mass, and I'm going to have to first convert to moles of calcium chloride. Once I'm in moles, I can cross over to my unknown. My known in this case is calcium chloride because I know how many grams of calcium chloride. My unknown is what I'm trying to find out, and I'm trying to find out sodium chloride. Once I go from mass of calcium chloride to moles, then I can use the balanced equation to give me the molar ratio between calcium chloride and sodium chloride. So this part I'm going to get from the balanced equation. And what's going to happen is I'm going to be converting, when I use the balanced equation, I'm going to convert from moles of calcium chloride to moles of sodium chloride. And then finally, I can look in my problem and I want to know how many grams of sodium chloride. So I'm going to have to convert grams of sodium chloride back into mass. And so just like over here, I'm going to use the molar mass from the periodic table. If I were converting back to particles, I would use Avogadro's number. And here I would use the molar volume. Now, if you aren't given grams, and you're not given liters, then you're going to be using Avogadro's number. Most stoichiometry problems, though, are going to go from mass of the given to mass of the unknown. And so most stoichiometry problems will follow this format, where we go from mass to moles of the given, from moles of the given to moles of the unknown, and then to mass of the unknown. So once I'm in moles of sodium chloride, then I can convert to grams of sodium chloride, which is ultimately what I want my answer to be in. Now I've got to set up a T-chart. And I'm going to set up a T-chart by taking my given and I'm going to carry down the unit of my given, and I'm going to carry up the moles. You can be doing the same thing that you did in mole conversions here. So here, whenever I have a little trick to remember is whenever I have moles in a different unit, the number 1 is going to go in front of the moles. Now, for this one, I've got to go to the periodic table and calculate the molar mass. The molar mass of calcium is 40.1 grams. And the molar mass of chlorine is 35.5 grams, but I have 2 chlorines, so that's going to give me 71 grams for a total of 111.1 grams. And so that's what's going to go here. This cancels out grams of calcium chloride. Now I'm going to carry down my moles of calcium chloride. And now I'm going from moles of calcium chloride to moles of sodium chloride. Whenever I have moles and moles, that's when I get the numbers using the coefficients from the balanced equation. So there's no number in front of calcium chloride, which indicates it's a 1, and there's a 2 in front of sodium chloride. What this means, I'm just doing a mole ratio. For every 1 mole of calcium chloride I react, I'm going to get 2 moles of sodium chloride. So moles of calcium chloride are going to cancel out. And now I'm going to carry down moles of sodium chloride because I'm going to do my final conversion factor, and I want it in grams of sodium chloride. I have moles and grams, so the number 1 is going to go in front of moles. Whenever I have moles in a different unit, 1 goes in front of moles. Sodium has a molar mass of 23 grams. And chlorine has a molar mass of 35.5 grams. So this is going to give me a molar mass of the compound of 58.5 grams. And so the moles of sodium chloride are going to cancel out. Now, to get the number part of my answer, I have to multiply and divide. So I'm going to multiply 45.2 times 1 times 2 times 58.5 divided by 111.1 times 1 times 1. Okay, when I multiply and divide all of this out, I'm going to get an answer of 47.6. And for my unit, the unit that's left is grams of sodium chloride. So what this means is if I start out with 45.2 grams of calcium chloride, because there's a mole ratio of 1 mole of calcium chloride produces 2 moles of sodium chloride, I'm going to produce 47.6 grams of sodium chloride from that amount of calcium chloride. Example problem number 2 asks us how many moles of iron 3 oxide will be produced if 5 moles of oxygen are present. So I know my given is 5 moles of oxygen. Since I'm already in moles, okay, I'm starting with moles of my given. I don't have to convert. I don't have to do any of this pre-conversion. I can go directly to calculating the moles of my unknown. And my unknown in this problem is iron 3 oxide. So I can go to moles of iron 3 oxide. And I want my answer in moles. So again, I don't have to convert to mass, particles, or volume. My answer is going to be right there. So what this means is that I only have one conversion factor. Sometimes we call this little chart a mole map. And your mole map, each arrow is going to be one conversion factor. So for this one, I would just take my given, 5 moles of O2. I'm going to carry down my unit, moles of O2. And I'm going to carry up moles of Fe2O3, iron 3 oxide. I've got moles and moles in my conversion factor. So that means I have to look at the balanced equation. 3 moles of oxygen produces 2 moles of iron 3 oxide. So I'm going to take 5 times 2 divided by 3. And that's going to give me 3.3 repeating. So we'll just leave it as 3.3. Moles of oxygen have canceled out, and I'm left with moles of iron 2 oxide. Sorry, iron 3 oxide. Our next example problem asks us, using the following equation, how many grams of iron 3 oxide are going to be produced from 5 grams of iron. So now my given is that I have 5 grams of iron, and I need to convert that first to moles of iron, because to go through the mole conversion, I have to be in moles. So I'm going to convert the grams of iron to moles of iron. Iron is my known. My unknown is this iron 3 oxide. So I'm going to have to first convert to moles of iron 3 oxide. And then I can look and I can see that my problem is asking for mass or grams of iron 3 oxide. So I'm going to have to convert to grams of iron 3 oxide. I'm going to set this up, 5 grams of iron. I'm going to carry down grams of iron to moles of iron. Since I have moles and grams in my conversion factor, a 1 is going to go in front of moles. I'm going to look at the periodic table and see that the atomic mass of iron is 55.8. So in 1 mole, I'm going to have 55.8 grams of iron. Now, I'm going to carry down my grams of iron have canceled out. I'm going to carry down moles of iron. Remember, I've got to make a conversion factor for each arrow. So this one's going to have 3 conversion factors. And I'm going to moles of iron 3 oxide. I have moles and moles in my conversion factor. So that's when I'm going to look at my balanced equation. The coefficient in front of iron is 4. The coefficient in front of iron 3 oxide is 2. Now my moles of iron cancel out. And now I can do my last conversion factor where I go from moles of iron 3 oxide to grams of iron 3 oxide. And I've got moles and grams, so the number 1 is going to go in front of moles. Iron 3 oxide, I have 2 irons, each at 55.8. So that's going to give me 111.6. And oxygen is 16.0, and I have 3. That's going to give me 48. So this is going to be 159.6. And my moles of iron 3 oxide cancels out and I'm left with grams. Now I have to multiply across and divide. 5 times 1 times 2 times 159.6 divided by 55.8 times 4 times 1. So this is going to give me an answer of 7.2 grams of iron 3 oxide. Our next practice problem is going to be how many grams of lead 2 chloride can be produced when 55.2 grams of lead 2 nitrate is mixed with an excess of sodium chloride. So remember, the first thing we have to do is get our chemical reaction written and balanced. So we're going to have lead 2 nitrate mixed with sodium chloride. And from that, we are going to produce lead 2 chloride and sodium nitrate. So I'm going to have to put a 2 here and a 2 here. And that's going to balance out. Now, I'm going to look in my problem for the number. My number is 55.2 grams, and it's 55.2 grams of lead 2 nitrate. So that's where my mole map is going to start. 55.2 grams of lead 2 nitrate. I'm in grams, so I have to first convert to moles. So I'm going to convert to moles of lead 2 nitrate. Now that I'm in moles of my given, I've got to go to moles of my unknown. My unknown is lead 2 chloride. So I'm going to go to moles of lead 2 chloride. And then I can convert to mass of my unknown, or mass of lead 2 chloride. I have 3 arrows, so that means I'm going to have 3 conversion factors. I'm going to set up my T-chart. And in my given box, I'm going to put my 55.2 grams of lead 2 nitrate. I'm going to carry down grams of lead 2 nitrate. And I'm going to carry up moles of lead 2 nitrate. I have moles and grams, so 1 is going to go in front of the moles, and I'm going to need to calculate the molar mass of lead 2 nitrate to get the number to go in front of grams. Okay, from the periodic table, I can find that the molar mass of lead is 207.2. And I have 1 lead in my molecule, my formula unit. I have 2 times 3 nitrogens, so I'm going to have 2 times 1 nitrogen, so I'm going to have 2 nitrogens. Each one is 14 grams. So that's going to give me a total of 28 grams from nitrogen. And then for oxygen, I have 2 times 3, or 6 oxygens. Each one has a mass of 16 grams. So that's going to give me 96 grams from oxygen. So when I add all this together, I'm going to see that the molar mass of lead 2 nitrate is 331.2. And my grams of lead nitrate cancel out. So I've done this conversion factor. Now I've got to go on to my second conversion factor. My second conversion factor has me going from moles of lead 2 nitrate to moles of lead 2 chloride. So I'm going to carry down the moles of lead 2 nitrate, and I'm going to carry up the moles of lead 2 chloride. I'm going to look at my balanced equation. Neither one has a number, so that means the coefficient for both of them is 1, and the moles of lead 2 nitrate cancel out. Now I'm going to carry down moles of lead 2 chloride, and I'm going to carry up grams of lead 2 chloride. I have moles and grams, so 1 is going to go in front of moles. And lead is 207.2, and chlorine, I have 2 of them. Each one is 35.5, So that gives me 71. So that's going to give me 288.2 grams. So now I've got to do my multiplication and division. 55.2 times 1 times 1 times 288.2 divided by 331.2 times 1 times 1. And so that's going to give me an answer of 48 grams of lead 2 chloride. Next practice problem is how many grams of aluminum oxide can be produced when 23.2 grams of sodium oxide is mixed with an excess of aluminum chloride. So I am going to form my balanced equation, and I'm mixing sodium oxide and aluminum chloride. And I'm going to produce aluminum oxide and sodium chloride. So now I've got a balance. And this is going to balance for me. Now, my given is in sodium oxide, so I'm going to take 23.2 grams of sodium oxide, and I'm going to first convert that to moles. Then I can convert from my given to my unknown. So I'm going to convert from moles of sodium oxide to moles of aluminum oxide. Then I can finally convert to grams of aluminum oxide. In the T-chart, in the given column, I'm going to put 23.2 grams of sodium oxide. Carry grams of sodium oxide down, then moles up. Moles and grams, one is going in front of the moles. Sodium, there's 2 of them. Each one has a mass of 23. Oxygen is 16. So that's going to give me a mass of 62. Grams of sodium oxide will cancel out. Now, I can go from my known to my unknown, my given to my unknown. And I'm going to do that by doing moles of sodium oxide to moles of aluminum chloride. Sorry, of aluminum oxide. No number in front of aluminum oxide, so that's a 1. And in front of sodium oxide, there's a 3. So moles of sodium oxide canceled out. And moles of aluminum oxide to grams of aluminum oxide. 1 mole Aluminum is 27. And there's 2. So that's going to give me 54. There's 3 oxygens. Each one is 16. So that's going to give me 48. So that's going to be 102. And now I'm in moles of aluminum, grams of aluminum oxide. So I'm going to multiply 23.2 times 1 times 1 times 102 divided by 62 times 3 times 1. Which is going to give me 12.8 grams of aluminum oxide. Okay, now I've got 2 problems for you to try. So stop the video at this point, work these 2 problems, and then come back to the video to check your answers. So the first try it yourself problem says how many grams of sodium oxide can be produced when 3.2 moles of potassium oxide is mixed with an excess of sodium chloride. So first of all, we're going to set up our balanced chemical reaction. And our chemical reaction tells us that sodium chloride plus potassium oxide is going to produce sodium oxide and potassium chloride. We have to put a 2 in front of the sodium chloride and a 2 in front of the potassium chloride to balance out the equation. My given is moles of potassium oxide. So since I'm already in moles, I don't have to convert to moles. So I'm going to go straight from moles of potassium oxide to moles of sodium oxide. Then I can convert to grams of sodium oxide. So I have 2 arrows in my mole map. I'm going to have 2 conversion factors. So your T-chart should look like what you see in the picture. And when you multiply and divide, you're going to get an answer of 198.4 grams of sodium oxide. Practice problem number 2 says how many grams of aluminum nitrate can be produced when 56.2 grams of potassium nitrate is mixed with an excess of aluminum chloride. I'm going to set up my chemical reaction. Aluminum chloride plus potassium nitrate yields aluminum nitrate plus potassium chloride. Balance it out by putting a 3 in front of the potassium nitrate and a 3 in front of the potassium chloride. My given is in grams this time, so I'm going to have to go from grams of my given to moles of my given. And then I can go to moles of my unknown and finally to mass of my unknown. I'm going to set up my T-chart as seen in the video. And when I multiply and divide, I'm going to come out with 39.5 grams of aluminum nitrate. Now, you will go on and work the 2 sets of problems. The first set where you're given the answer and you don't have to turn them in, and then the second set where you do turn them in. If you have any trouble working these problems, send me an email and we can set up a time where you and I can meet in the classroom and I can help you work through the problems that you're having. Okay, well, have a good week and I will see you for assignment 10. Bye.